Hello everyone. In this video we will see the specifications of robot coordinate system used in robot. So first we will see the specifications of robot. So first is the speed of motion. So this refers to how quickly a robot moves, measured as the amount of distance it covers in a set amount of time. This speed is typically expressed in units like inches per second or meters per second and is measured at the wrist of the robot. The speed plays a crucial role in determining how long it takes for the robot to complete a task and must be considered in conjunction with accuracy and the distance the robot needs to travel. Okay. Next specification is load carrying capacity. So this is often known as the maximum weight a robot can handle is determined by the robot's weakest position, typically when its arm is fully extended. This capacity includes the weight of the end effector, the tool or hand it uses for task. The engineers also consider factors like precision, weight, and cost when determining a robot's payload capacity. It's an important metric to ensure that the robot can safely and effectively perform its task. Next, spatial resolution in robotics is the smallest increment of movement that a robot can make within its working area. Imagine it as the tiniest step the robot can take. Okay. This resolution is limited by both the robot's control and capabilities and its mechanical imperfections. And the control resolution refers to the individual steps the robot controller can manage, determining how closely it can move from one point to another within its range of motion. Mechanical inaccuracies like flexing, gear slack, or hydraulic leaks can affect this precision. So, in simpler terms, it's all about how precisely the robot can move, considering its own capabilities and imperfections. Okay. Next is the accuracy. So, accuracy in robotics is all about how well a robot can place its end, okay, like its hand or the tool. So exactly where it's supposed to within its operating area. It's like aiming for a bullseye on a dartboard. The closer you get to the center, the more accurate you are. Okay. However, a robot's accuracy can vary across its workspace, just like how you might be more accurate at a particular distance on the dartboard. This variation is known as the error map. The robot's ability to be accurate can also depend on how much weight it's carrying. Okay, heavier loads might affect its precision. Accuracy is an absolute measure telling us how well the robot can hit its target, and it's influenced by mechanical imperfections in the robot's components. The next is the repeatability. So it's like how consistent a robot can be in hitting the same spot over and over again. So think of it like a basketball player making free throws. If they can consistently aim for the same spot on the hoop, they are highly repeatable. But here is the twist: just because they can't hit the same spot consistently, so doesn't mean they are always right on target. Okay. So a robot can be good at hitting the same point repeatedly, that is repeatable, but doesn't necessarily mean it's always perfectly accurate. Okay. So mechanical quirks in the robots are usually what cause these slight variations in repeatability. Okay, next is precision of robot movement is kind of like how well it can hit a specific target repeatedly. It's determined by a few factors, including how detailed its control is. So, like this, like a difference between being able to hit a target within an inch or within a millimeter. Okay. So, how accurate whether it's consistently on the bullseye, and how well it can keep hitting that same spot. That is repeatability. So, all of this matters when the robot is reaching out as far as it can, like a basketball player trying to make the perfect shot from the far end of the court. And next is precision in measurement is about how finely you can report a value. It's kind of like how accurately you can measure and express a number. For example, saying something is like 4.71298 is more precise way of expressing it just around to 4.7. Okay, so precision in measurement is all about giving more detailed and specific information. Next, you could see here the pictorial representation of accuracy, precision, and repeatability. So, in first figure, accuracy and precision are high. Okay, so in the second picture, so you could see precision is high, where it is hitting in the same target, but accuracy is low. Okay, in third picture, you could see it is hitting the target, but accuracy is high, the precision is low. Okay, it is not at this same location. And in fourth picture, you could see both are low. That is no precision and no accuracy. No accuracy. Next is about axis. Okay, so think of robot axis as the different parts of the robot's arm that can move. These parts are connected by joints which allow them to twist and turn. Most industrial robots have six of these axes, giving them a lot of flexibility in how they can move. Okay, now imagine um, each of these axes has a limit to how far it can move. So it's like saying you can bend your arm from your elbow, but only up to a certain point. Okay, so this here have the range of motion for each axis is measured in degrees, just like a circle. So when you look at the robot specifications, you will see how many degrees each axis can move, either in a positive direction or a negative direction. So these degrees tell you how flexible the robot's arm can be. Okay, that's about the robot motion range. And next is the robot motion speed. So imagine a robot with the different parts that can move. Each of these parts can move at its own speed, and this speed is measured in degrees traveled per second. So it's like saying how fast your car can go in miles per hour. Okay. Now when we talk about repeatability, we mean how well the robot can go back to the same spot multiple times. So think of it like shooting a basketball into the hoop, as I said earlier. A robot with good repeatability can make the same shot over and over again, hitting the bullseye. But not all robots are equally good at good at this, and it can vary from one robot model to another. Okay. So next, when we talk about payload, we are referring to how much weight a robot's arm can carry. This is an important number to consider, and it includes the weight of anything the robot is holding, like tools or objects. Now, the robot mass, simply how heavy the robot itself is, just the arm part. Doesn't include the weight of the robot's brain, which is the controller. So it's like knowing how much the robot's body weighs without counting the weight of its brain. Okay. So next is about the V reach, H reach. Okay, that is vertical reach and horizontal reach. So here, that is V reach of a robot tells us how high it can reach when it extends upward from its base, like reaching for something on a high shelf. Okay. And H reach is about how far the robot can stretch its arm out, measured from the base to the wrist, like when you are trying to grab something across the table. Okay. So now when we talk about the structure of a robot, we are discussing the different ways the robot's arm is built. It's like saying whether it's a straight arm or a jointed one or any other design. Okay, you could see here in the picture. It's covering vertical reach and horizontal reach. Next, these are about various robot mounting applications. And next we'll see about the robot configurations. Okay, here we have 4 types of configurations. We'll be seeing one by one. So first is the Cartesian coordinate robots. Okay, It is represented as 3P, that is 3 prismatic joint. Okay, you could see here as SSS. It is represented as sliding joint as well, or prismatic joints. So here we call it as SSS or PPP or 3P or 3S. Okay, anyway it can be represented. So this Cartesian coordinate robots with the 3P, 3 prismatic movement, have arms that can move in straight lines along 3 different directions, just like sliding or prismatic motions. So they are sturdy and precise, making them great for tasks like picking up and putting things down. Okay, think of them like super accurate arms that move in straight lines. Okay, so IBM's RS1 and Sigma robot are the examples for this. So you can see here the 3 prismatic joints X, Y, and Z. And next, second configuration is the cylindrical coordinate robots. You could see in the picture. Okay, so these are represented as TPP or TSS. Okay, so you have 2 linear and 1 rotary. For rotary, it is represented as T, and for linear, it is again prismatic or sliding only. Okay, so that is why it is represented as TPP or TSS. So this has 2 linear movements and 1 rotary motion. So they are good for handling objects during manufacturing, but they can't quite reach things on the floor as it is cylindrical type. They are not as agile as some other robots and may struggle with rapid movements. Okay, imagine them as robot arms with 2 straight moves and 1 spin. Okay, so an example is the Versatron 600. It will show you the video of the cylindrical Cartesian robot first. You could see the 3 prismatic movements. For pick and place applications. Next we will see the video for cylindrical coordinate system. You can see 1 rotary motion and 2 linear axes. So next configuration is this spherical coordinate or polar coordinate robots. Okay, so these have 1 straight movement and 2 rotations. So it is represented as TRP or TRS. Okay, T and R for rotations and 1 P or S for sliding movement. Okay, so they are great for working with objects in the manufacturing, and they are good at picking up things from the floor. However, they may not be the quickest at changing directions. So picture them like arms with 1 reach and 2 spins. Okay, the Unimate 2000B is an example for that. We'll see the video for this.
There are 4 main types of robotic arm geometry. Rectangular can rotate in 2 directions and move linearly in 1, and thus are given the designation of 2RP. The robot has base rotation, shoulder rotation, and prismatic or linear motion at the arm.
You can see 2 rotations.
This type of robotic arm is most often used in machine tending, material handling, welding, painting, coating, and assembly tasks. Robotic arms with spherical geometry have rotational movement in 2 directions, rotational movement at the base and rotational movement at the shoulder. Spherical arm geometry robots also have linear motion in 1 direction, typically the reach of the arm. Spherical arm geometry robots have a mostly spherical work envelope at their outer reach, but are limited by the linear reach of the arm and the rotation of the shoulder joint. The shape of the robot's inner work envelope is almost conical and does not become a sphere until the arm extends.
So work volume is
Spherical
spherical
arm
work volume.
geometry robots typically have a very long reach.
So next coordinate, that is configuration, is revolute coordinate or articulated coordinate robots. Okay, so they have rotatory movements around 3 separate axes. So they are suitable for managing parts and components in manufacturing systems. However, they may not be as steady and precise as you would like. Okay, think of them as arms that can rotate around in various ways. So examples include T3 and Puma. Okay, you could see here this articulated coordinate robots configuration.
174 Excel formulas.
Hold
Can you
on.
believe it? Yes. Now you can use 170.
These are articulated robots. You see the working here. So these are about the revolute coordinate robots. So we have a rotary movement about 3 independent axes. Okay, X, Y, Z. So these are the configurations of robot. So Cartesian, cylindrical, spherical, and articulated. And its work volume. Okay, for Cartesian, work volume is given, and for cylindrical, spherical, articulated. The second row pictures represent the work volume pictures of each coordinate. Okay, each configuration of the robot. Next is about the what is a workspace of manipulators. Okay, so workspace of a robot is like the area it can get its hand to. Okay, so here first a reachable workspace is the part it can touch in one specific way, while the dexterous workspace is all the different ways it can reach out and touch things. Okay, think of it like your hand. You can touch things in many ways. Okay, but with your hand in one fixed position, you can only touch what's right in front of you. Okay, you could see the difference between the dexterous workspace and reachable workspace without hand. Okay, so next, so these are the workspace of configurations. So workspace, first one is the workspace of Cartesian coordinate robot. Okay, since it has linear movements, you could see here vertical stroke you have, horizontal stroke you have. Okay, next cylindrical coordinates. So you have a one rotation. You could see here in the picture. Okay, how its workspace varies. And this is the workspace of the spherical coordinate and articulated coordinate robot. Okay, so this is an overview of the workspace for Cartesian coordinate robot. What is the structure and its workspace? For cylindrical robot, what its structure, okay, and its workspace. Spherical robot, its structure and workspace. Okay, so we have seen articulated, revolute, and its workspace. And apart from this 4-degree of freedom, you have a SCARA robot. Okay, a SCARA is also you have both linear as well as rotary movements. Okay, that is also articulated robot. So, and its workspace. So this is overview of workspace. Next is the robot coordinate system. Okay. So the robot's main joints have a simple job. They may help the robot to a specific spot in space. So robots can move in different ways to do this. Some move straight in line, some rotate like a wheel, and others use a mix of both depending on how their joints are set up. Okay. So here comes the Cartesian coordinate, revolute, that is revolute coordinate, cylindrical coordinates or spherical coordinates. Okay, it depends. So we'll see again one by one. Already we have seen the configuration. Just we'll see the overview of this Cartesian coordinate system. So these Cartesian robots have three joints that move in a straight line, allowing them to go up and down, left and right, and forward and backward. Okay, this is handy for tasks like moving things around horizontally or stacking objects in bins. These robots are easy to program, can do the same task repeatedly very precisely, and can and can lift heavy things. Okay, but they need more space to work compared to some other types of robots. Okay, next is we'll move on to cylindrical robots. So they have two joints that move in a straight line. Okay, that is horizontal and vertical, and one joint that allows them to rotate at the base. The range of motion looks like a cylinder. These robots are commonly used for tasks like picking up objects from conveyor belts or handling small parts that don't need a lot of side to side movement. They are good at working against gravity, easy to program, can lift heavy objects, and can access tight spots. Okay. However, they usually can't reach the ground. Okay. This is about the cylindrical coordinate system. And next is the spherical coordinate system. So these spherical robots have two joints that can rotate and one that moves in a straight line, and their motion is defined using here theta 1, theta 2 and z coordinates. These robots are typically good at lifting heavy objects and are easier to design compared to robots with all rotating joints. They work well for tasks like loading and unloading machines. Okay, like punch presses have a good range and can access tight spaces. However, their ability to move vertically is somewhat limited here. And next is the revolute coordinate system. So revolute robot consists of all rotational joints, making it highly flexible. It also features a parallel linkage between the base and upper arm, which allows precise control of the shoulder and elbow joints by motors located in the base. Okay. This design reduces the weight at the elbow joint and makes the robot more compact, requiring less workspace. The robot's stiffness and lighter forearm enable faster and more accurate movement of the end effector. However, there are a couple of drawbacks to revolute robots. When their arms reach their maximum extension, their load carrying capacity is reduced here. Additionally, they require advanced computer control capabilities to manage the coordinate system and articulated motion, so which can be a complex task. Okay. And next is the wrist coordinate system. So wrist assembly is connected to the end of the robot arm. The end effector, which is the part of the robot that interacts with objects or perform tasks, is then attached to the wrist assembly. Okay, the main purpose of the wrist assembly is to adjust and position the end effector correctly. Okay. The body and arm of the robot together determine the overall or global position of the end effector within its workspace. And this coordination between the body, arm, wrist assembly, and end effector allows the robot to perform the task with precision and efficiency. Okay, so this is about the wrist coordinate system. And finally, we'll see the coordinate comparison. So each type of robot has its unique advantages. Certain robots are known for their exceptional repeatability and ease of programming. Cylindrical robots are also relatively easy to program and have good lifting capacity. Okay, on the other hand, spherical and revolute robots are particularly great at reaching out and being flexible in their movements. Okay, revolute robots can even mimic human arm motions, making them suitable for tasks like paint spraying, which require more human-like approach to teaching. Okay, these are the coordinate comparisons. Okay, so we have seen the technical terms, okay, for specifications of the robot and configurations of the robot. Okay, thank you.